0.40 meter branch duct leaves a 0.30 by 0.60 main duct at an angle of 60 degrees. The air temperature is 20 degrees Celsius. The dimensions of the main duct remains constant following branch. The flow rate upstream is 2.7 and the pressure is 250 Pascal. The branch flow rate is 1.3 cubic meter per second. What is the pressure downstream in the main duct? Note, at 20 degrees Celsius, the density is 1.2041 kilograms per cubic meter. Okay, let's visualize our main duct with a branch duct. Okay, so let's start with our upstream point, which has a pressure of 250 Pascal and a flow rate of 2.7 cubic meter per second. The branch flow rate, let's denote that as point B, has a flow rate of 1.3 cubic meter per second. So obviously, 1.3 came from the 2.7. So that means at the point downstream, our volume is now 2.7 minus 1.3. So that will be 1.4 cubic meter per second of flow rate at the downstream point. So the question here is, what is the pressure at that point on the downstream in the main duct? Okay, so using the analysis of our conservation of energy, so we have here this formula. The difference of our downstream and upstream pressure is equivalent to density times upstream velocity squared minus downstream velocity squared over 2. But since there is a branch duct at a certain angle, there will be some pressure loss. And that pressure loss has a derived formula of density times Vd squared over 2 times 0.4, a factor, times 1 minus downstream over upstream velocity quantity squared. Okay, so let's identify our given. Okay, our unknown is the downstream pressure. We have the upstream pressure is 250 Pascal. We have our density. And for our pressure loss, density is also required. But we don't have yet our upstream and downstream velocities. So before finding our downstream pressure, we must identify first our velocities at the upstream and at the downstream. As you can see, our volume flow rates are provided, as well as the dimensions of our ducts. So obviously, we have a formula for the volume flow rate where area is given, and that is Q is equal to area times velocity. So meaning, if I am to find the velocity, it is equivalent to the ratio of the volume flow rate and the area. For example, if I'm to find the upstream velocity, so I need the volume flow rate at the upstream and the cross-section area upstream. So that will be, at the upstream, our volume flow rate is 2.7 cubic meter per second over our upstream area. So at the upstream, our cross-section area is the same area as our main duct, and that is 0.3 by 0.6 meters. So our upstream velocity in meter per second is 15 meters per second. So using the same formula for the downstream, this will be downstream velocity is equal to the volume flow rate at the downstream over the area of the downstream. So at the downstream, our volume flow rate is 1.4 cubic meter per second divided by the area downstream. So the cross-section area at the downstream is the same as the cross-section area at the upstream. So that is 0.3 and 0.6. So our velocity downstream is 7.78 meters per second. And now we have our upstream and downstream velocities. Okay, so let's use this first formula. So our downstream pressure is unknown. minus upstream pressure, which is 250 Pascal, is equal to the density 1.2041 times upstream velocity minus downstream velocity all over 2 minus the pressure loss, which has the same formula as this one, is density times downstream velocity squared over 2 times 0.4 multiplied by 1 minus downstream over upstream quantity squared. What is our downstream pressure? Which has the same unit as the upstream pressure, so that is Pascal. The answer is 346 Pascal. In sensible cooling process, the moisture content does not change. Determine the sensible heat of a 5 pound of air having a dry bulb temperature of 70 degrees Fahrenheit and a humidity ratio of 0.0092 pound per pound. The latter corresponding to a dew point temperature of approximately 55 degrees Fahrenheit. So we are asked here to find the sensible heat, which has a formula of Q is equal to mCp delta T. Okay, we have here mass of 5 pounds, Cp of air, that is 0.24 BTU per pound Rankine. And then our changes in the temperature are 70 minus 55. And the change in Fahrenheit is also the change in Rankine. And pounds is also cancelled. What is our Q? The answer is 18 BTU. As you can see, the real answer is not on the choices, meaning there must be something wrong in the problem or in the answer key. Okay, to be able to answer this problem, this particular problem, so we must omit the final factor. So we're solving this using M, that's 5, Cp of air, that's 0.24, but the temperature included only in the solution is the initial temperature, which is the dry bulb temperature, 70. What is our Q? So the answer is 84 BTU. 94. The dividing point between the high pressure and low pressure sides of the refrigerating cycle occurs at the expansion valve. Next one, determine the coil phase area required to maintain a phase velocity of 400 feet per minute. If the airflow rate over the coil is 2,100 cubic feet per minute. Recalling, the volume flow rate is equivalent to the area times the velocity. In this problem, we are asked to find the area, meaning this is the ratio of the volume flow rate and the velocity. Okay, the volume flow rate is 2,100. And that is cubic feet per minute over the velocity, which is 400. And that is feet per minute. We cancel out minutes and we can cancel out one of the foot. So our area will be in square feet. Answer is 5.25 square foot. The total energy in a compressible or incompressible fluid flowing across the section in a pipeline is a function of flow energy, kinetic energy, height, and internal energy. Next one, the mass of an outside air at 50 degrees Celsius in an air conditioning unit is 60 kilograms. Find the temperature after mixing if the outside air mixed with 40 kilograms with recirculated air at 35 degrees Celsius. Okay, we have here a mixing of outside and recirculated air. And as we all know, if those two are mixed, so that is the supply air. So using the air mixing formula, we have the mass of the outside air, that's the temperature of the outside air, plus the mass of the recirculated air plus the times the temperature of the recirculated air is equal to the mass of the supply times temperature of supply. And the required here is the temperature after mixing or the temperature of the supply air. Okay, let's use our given. Okay, the mass of the outside air is 60 kilogram, while its temperature is 50. Plus, mass of the recirculated air is 40, while its temperature is 35. For the mass of the supply, so we will be using our conservation of mass. So take note that the mass of the supply is the sum of the outside air and the recirculated air. And our unknown is the temperature of the supply. What is our answer in degree Celsius? The answer is 44 degree Celsius. The ratio of the density of a substance to the density of some standard substance is called the specific gravity. Calculate the heat transfer per hour to a solid brick wall 6 meters long, 2.9 meters high, and 225 meters thick when the outer surface is at 5 degrees Celsius and the inner surface is 17 degrees Celsius. The coefficient of thermal conductivity of the brick being 0.6 watts per meter Kelvin. So we have here the heat transfer through conduction on a plane wall. The formula for that particular heat transfer is Ka delta T over X, where K is our thermal conductivity, A is our heat transfer area, delta T is the change in the temperature, while X is the thickness of our wall. And let's identify our given. Our K is the thermal conductivity, 0.6 watts per meter Kelvin. Area, so this is the product of the length of the wall and the height of the wall. That is 6 meters times 2.9 meters. That is square meters. Our change in the temperature, that is 17 minus 5 all over. The thickness is 225 and that is millimeters. If we divide that by 1000, that will be meters. Keep that loud, meters. As well as the change in Celsius, which is the same as the change in Kelvin. So our final answer here is watts or joules per second. But we are asked here for the heat transfer per hour. So we must multiply 3,600 seconds per 1 hour. Cancel. So the remaining answer will be in joules. But as you can see, the choices are in kilojoules. So we must integrate another conversion factor. We know that 1 kilojoule is equivalent to 1,000 joules. What is our heat transfer per hour? The answer is 2,004.40 kilojoules per hour. The speed with which a liquid escapes from a vessel through an orifice is given by Torsell's theorem.